This is problem 52 from chapter 18, and we are asked to analyze this series and parallel combination circuit. The first question asks to find the equivalent resistance between point A and B. And to do that, we use Kirchhoff's current law to create a formula to solve for our equivalence of parallel resistors. As you can see right here, the voltage, the total current is equal to the current across the summation of currents across each parallel resistor. So we use that for this first nested parallel circuit. 1/4 ohms plus 1/8 ohms to the -1 is equal to 2.7 ohms roughly. And since we could find the equivalent resistance of that parallel circuit, now we can simply just add the two series together to get 6 ohms. As you can see, we also did that step for the top branch, simply adding them together. 2 plus 1 is 3. So we have 3 at the top and 6 at the bottom now. Now we only have one parallel circuit in this circuit, so we use our equivalence for parallel resistors once again. 1/3 plus 1/6 to the -1 is 2 ohms. And now we have a clean and simple series-only resistor circuit, and we can add them together to get 3 ohms as the final equivalent resistance for the circuit. For part B, we are asked to find the current through the 1 ohm resistor, which is connected directly to point A. And to do that, we find the total current using Ohm's law and the given EMF of 18 volts. We divide the total EMF by our equivalence to find the total current to be 6 amps. And since we know current through series resistors is equivalent, we know that the total current is equal to the current going through this first series resistor. For part C, we are asked to find the current across the 8 ohm resistor, which is a little bit more difficult because this is the nested one. We can't just simply find the total current and set it equal to that. So we kind of have to work backwards, going from where we finished to going to where we started. So for this, we know that the total current across our equivalence is 6 amps. So we can find the voltage drop across this 2 ohm resistor. And the voltage drop across that 2 ohm resistor is equal to the voltage drop from this node to this node. And to find that, we use Ohm's law. Since we know 6 amps is going through these two, we do 6 amps times 2 ohms to find the voltage drop across this resistor to be 12 volts. So if we know 12 volts is the voltage drop across this node to this node, we can find the current through this bottom branch 6 ohm resistor. And we can find that to be 2 amps using Ohm's law again. And now we go to this expanded bottom branch, which we got from this right here, which is right here. And we want to find now the voltage drop across this 2.7 ohm resistor. Since we know the current going through these two, we can find the voltage across this. And we find it to be 5.4. And now that we know this 5.4 to be the voltage drop across this resistor, or this node to this node, we can find the current through, because if we know the voltage and the resistance, we can find the current. So to find that, we know that the voltage drop is 5.4 divided by 8 ohms to find 6.75 amps. And since we have to show our face, I'm right here.